All right. Chapter 13, question 1. All right, this might probably be your hardest homework set that you've had all semester, but we are at the end. These are important to know. Getting through them is important for next semester for Physics 2. We'll have a lot of similar products or similar problems like this as well in Physics 2, so it's good to get to know them. Here, we're going to start off with a 200 kilogram object and a 500 kilogram object. They're separated by a distance of 4 meters. So I drew a 200 kilogram object, a 500 kilogram object, and I placed 4 meters between them. Question A says, find the net gravitational force exerted by these objects on a 50 kilogram object that is placed midway between them. All right, so for part A, I placed a 50 kilogram object halfway between the two masses. Okay, so that each of the radiuses then would be 2 meters away. Okay, so for this, we're looking for gravitational force. We'll go ahead and use our gravitational force equation, the new one that we have for this chapter, where we have G. Okay, so that is a Newton's gravitational constant, 6.67 times 10 to the negative 11th. We need 2 masses, and here we have 3, so we'll have to break this down. The first mass will want to pull that 50 kilogram object towards it. It'll be a traction, so it'll try to pull it this way. The other mass is larger, and it will also try to pull that object towards it. So there's going to be some conflicting vectors here. So we'll have to figure out what both of them are, figure out which one wins or which one dominates, and then there'll probably be a minus or a difference taken to see what the net force is. So let's work with this one first. This first mass, I'm going to call that 200 kilograms. So we'll put that in. And the other mass I want to know is the 50 kilograms. So I want to find the attraction between just these two. So 200 and 50. 200 times 50, sorry. 200 times the 50. And then they're both 2 meters apart. So the radius here is going to be 2 meters. And that has to get squared because it's r squared. If you calculate this, you should get 1.67 times 10 to the negative 7 newtons. Okay, so small amount of gravitational attraction because, again, really small masses, small distance. This equation is generally used for large, celestial bodies or something really big, but it absolutely does work for small objects as well. So we just have really small forces. For the second force, we're going to use the same equation. So we have the same constant, 6.67 times 10 to the negative 11. This time, though, our mass is 500 and 50. So we have the 500 kilogram mass and the 50 kilogram mass because we're going to find this attraction. It has the same radius, so 2 squared on the bottom. And if we calculate this, we get 4.17 times 10 to the negative 7. And again, it's in newtons. So we see that this one is larger, which is probably what we should have expected, being that this mass is bigger, it'll have more gravitational attraction. So this number is larger. So we need to minus the 1.67 from the 4.17. And if we do that, we should get a net force of 2.5 times 10 to the negative 7 newtons. But force is a vector, so we also need to put a direction on that. And the way I drew my problem, it will end up pointing in the positive x direction, but you may have drawn yours in a different orientation. Either way, that's fine. If to take care of the direction, we can just say that it's towards the 500 kilogram mass. And then we know we're right no matter how we drew it. Towards the 500 kilogram mass. Part B gets a little tougher. Part B says, at what position, other than the obvious answer of infinitely far away, can we place that 500 kilogram object so that it experiences a net force of 0 from the other two objects? So what I want to do is move this object around and find out where these two forces are equal to each other. Okay, so some things to consider. This object, I want these forces to cancel each other, so I want them in opposite directions. So the object will have to stay between the two objects. For instance, if I took the object and I put it over here, then both of these masses would be pulling in the same direction, and the vectors would never cancel. They'd actually add to each other, and they'd be both pulling in the same direction. Same if I did it on this side. So I need to find a place in here where I can place the object where it will get pulled to this object the same amount as it gets pulled to this object. So we saw here that this one was larger because that mass is larger. And so what we can do is we know that that needs to shrink. That radius to the 500 kilogram mass needs to shrink, and it needs to increase the radius to the 500 kilogram. So what that'll do is by changing the denominator, it'll increase this number and decrease this number. And we're going to try and get those two to match. So this is a bit of a math exercise, not quite like something we've done before in the class, but we have to think about this. So the distance for radius is, we're going to have to make one up here. We're going to have to use x for right now, because that's what we need to solve for. We have to figure out what the distance is. So I'm just going to call it x. And being I know this is 4 meters, it already predetermines what the other one must be. So if you wanted to go through the entire math problem here, we could call this one x, we could call this one, I don't know, d, for instance. But then you would have that x plus d has to be 4 meters, solve for d, and you will get 4 minus x. Okay, so if this one's 1 meter, then it instantly makes this one 3 meters. Okay, so it's not a free variable, it's tied, it's linked to whatever x is. Hopefully that makes okay sense. Why I have them labeled as x distance and 4 minus x distance, because wherever you move. Okay, so now that we have that, what we want to do is set these two equal to each other, because we want them to cancel. So I've got that here on another paper. This one was a bit long, and I've already done it out to save some time, because it's going to be a long video already. So I have the two equations. I have g, m1, which was 200, and I have m2, which is the 50. Okay, so I left g and I left m2 alone. And this distance between those two is going to be x, so I have x squared. I'm going to set that up equal to the other one, which also has a g. That mass is 500. The other mass, again, is just 50. You can put it in if you'd like. And that radius is going to be 4 minus x. And then that has to get squared. The whole thing, not just x. The whole thing needs to be squared. And now that we've got that equality, we can see that g cancels out. The other mass cancels out, doesn't matter. And the only thing that we have left is 200 over x squared is equal to 500 over 4 minus x squared. So I'm going to cross multiply so I can get rid of these fractions, because we don't want to deal too much with fractions. So if I do that, the 4 minus x squared comes over to the other side. So 200, 4 minus x squared is equal to 500 times x squared. Okay, so now we're at this. So I'm going to simplify a little bit further. I'm going to divide both sides by 200, and that'll bring me down to this. So I have 4 minus x squared, and 500 divided by 200 is 2.5 x squared. Okay, now I got to try and combine all my x's so I can solve for x. And this one gets a little more tricky. I need to go ahead and bring that square into the parentheses. So to do that, the first number is going to get squared, so 4 is going to get squared. The second number gets squared. You'll see x is going to get a square, and then it's going to also bring that exponent down inside, so I'll have 2 times 4 times a negative x, which will give me a negative 8x. Okay, so this should be standard math. Hopefully everybody is on board with that. And that's equal to 2.5 times x squared. All right, I've got x's and I've got x squared. There's no getting around this one. I have to put it into the quadratic equation. So I'll write this so that the quadratic equation makes more sense, which means I will minus the x squared to the other side. I'll have 2.5 minus 1x squared, leaves me with 1.5x squared. The negative 8 can get added to the other side, so I'll have plus 8x. And then the 16, 4 squared, 16, that has to be minused to the other side. So I'll get a negative 16, and that's my C property. So the quadratic equation is x equals to negative b plus or minus square root b squared minus 4ac all over 2a. So there's a little song to remember that by, but this is just a very basic quadratic formula equation. I'll throw it on the formula sheet if you need it, and we'll go ahead and we'll use this one. So I'm just plugging in my formula. Negative b would be this negative 8 plus or minus b squared, well 8 squared is 64, minus 4 times a times c. If you take 4 times 1.5 times a negative 16, you'll get a negative 96. And then all that's put over 2a. 2a was 1.5, so we end up with a 3 down below. And then we just start simplifying. This square root turns out to be 11.65. I rounded it, but 11.65. And so we'll have -8 plus or minus this number. So when I add them, when I do the addition, I get a positive 1.55. When I do the subtraction, I get a negative 6.88. So I get two answers. And how do we figure out which one we want to actually use? Well, both are actually still correct as far as the quadratic equation goes, because that's what it gives you. But they're not quite correct for our problem. The positive 1.55 puts the 50 kilogram object closer to the 500 kilogram object, which is what we want. Okay, so this gives us 1.5 from here to here. So which means we're going to have a large gravitational pull this way, and we are going to have a gravitational pull this way, but the distance has increased as such that these two should cancel each other out. They'll be the same, of course, that's what we just figured out. They'll be the same, but they're in opposite directions, so they'll cancel out. So at 1.15, we know then that the force is equal to 0. The sum of the forces is 0. So the 1.5 is actually what we are looking for. Okay, so that's our answer for this one, is 1.55 meters. The negative 6.88 is interesting because that says that we would have to take our planet, or our 50 kilogram mass, and we would have to move it way over here, so that this is negative 6.88 meters. Okay, so why do that? Why move it way over here? Well, it doesn't know that one of our vectors is positive and one of them is negative. So at this stage, this attraction to the right, due to this object, is the same amount as the attraction to this object. Because this one's bigger, it'll have a higher attraction, but these will be the exact same force being pulled to both the objects. Now in this case, whatever that force is would add, it would double. And we don't want that. We want them to cancel. So that's why our answer is 1.55.